should get started because if I don't finish before lunch, I think you guys are gonna hate me. So let's get started. So welcome to the Distributed System talk. My name is Yifan. I'm a student at Northeastern University. And I want to start this talk by having a poll. So raise your hand if you're a Kafka user or know someone, where did it go? Or know someone who know how to use Kafka. This still works. Okay, a good amount. I encourage you to look around and raise your hand if you can describe one of the consensus algorithms that's used in the distributed systems, or if you know someone that could describe the whole process. Okay, and look around, please. So the gap between the first round where people raise their hand when they think that when they know that they are distributed system users versus the second round where people can actually describe the consensus algorithm that's used in the distributed systems is the gap that I want to close today. So the goal of my talk is to help people who are distributed system users to understand better how consensus algorithms works in distributed systems. Well, when we talk about distributed systems, let's first define what it is. So basically, there are components. There are components that work together and that locate on different parts of the. It went away again. On the network, and they communicate with each other by passing messages with each other, and they communicate and coordinate with each other that way. So during our day-to-day life, we use a lot of things that are related to distributed systems. For example, the web. The web browsers are clients that communicate with the web server. The servers will send information to the clients via HTTP protocols. So that's a great example of distributed systems. And we also use DNS and BitTorrent. Those are also examples of distributed systems. So there's a fun fact about distributed system in the early years. In 1920s, American Airlines has this central office where they have a stack of cards for each flight. And the stack of cards marks how many seats that are sold and how many seats that are not yet sold. So the travel agents will call in and check if a seat has been sold. If not, they will purchase the seat from the central office. And the central office will then mark the seat as sold. So this is a very early example of how a distributed system works. So distributed systems are great. They help us to solve a lot of problems, and we need them in our day-to-day life. But there are also significant challenges that we need to deal with when we work with distributed systems. For example, how do we face the challenge of lack of global knowledge? So since we're working with different components, different servers, there's no single server that has a global view of everything. So we know about our own state machine, we know what's going on in our machine, but we have no idea of everything, all other machines around us. So how do we know that? How do we exchange information between machines? How do we make sure that the informations are up to date? And how do we detect inconsistencies? Also clock skew. So since we're working with different machines will have their own time. We might have a clock skew, and when we receive duplicate and delayed messages, how do we know what happened before what? And there are also consistent issues. How do we know, if there are certain concurrent operations that's happening on one single object? How do we ensure this object is consistent? And how do we know if there is any inconsistencies? How do we deal with conflicts? So Leslie Lamport has said a distributed system is some computer in the network. Their failure could cause your own computer unusable. So obviously the components of machines could hugely affect each other. I don't know why this thing keeps going off. Sorry about that. So the components could hugely affect each other. So how do we really tolerate the failures of components? By tolerate, we mean how do we detect the failures? How do we handle them? How do we recover from the failures? So all of the above, most of the above issues can be solved by implementing consensus algorithms on machines. And there are two very popular consensus algorithms on the machines. One is called Raft and one is called Paxos. It's okay, you can just listen to me. Don't have to look at the slides. And consensus algorithms, they help machines to achieve consensus between each other. And it helps our machine to be fault tolerant. It helps our machines to keep its integrity and availability, help us to process requests, process and execute client commands. So let's first take a look at Paxos. Paxos, compared to other consensus algorithms, has a rather colorful background. It was first designed by Lynch and Liskov. They designed and implemented this algorithm. However, they couldn't find provide a mathematical proof of proving why this algorithm works. So Leslie Lamport then discovered this paper and looked at it and was like, all right, I'm going to write something that will definitely prove this wrong. But then he accidentally proved it right. So he wrote this paper called The Part-Time Parliament that has a very cute story inside about the island of Paxos and trying to describe how it works and why it works. And so he submitted this paper trying to get it published. But there was one problem. The people who read the paper at the time couldn't really understand what he was talking about. So they rejected the paper. And he tried so many times. After 10 years, he finally got it published. And it seems like people at the time didn't really understand the significance of Paxos because most people can't really understand what he's talking about. So one day, sorry?
How old are those papers?
Well, the paper was published in 1980s, I believe. And you can ask, also, everyone is welcome to ask questions at the end. I just want to finish on time so that we can all go eat lunch. So he then went to a conference, and people were asking, like, oh, I know you published this paper called Paxos something. Can you just describe to me how it works? I don't really understand your paper. And he explained to people how Paxos works. And then people understood, and he was like, oh my God, I'm going to write another paper and called Paxos Made Simple. So he published this paper which describes basic Paxos. And people then started to understand, okay, what is Paxos and how it works. And then later he wrote about multi-Paxos, which is another version of Paxos, basically basic Paxos and complexity on top. So I'm not making this up, just to prove he actually wrote the story in the abstract of Paxos Made Simple paper, explaining the story of him explaining how Paxos works. So go read it, it's really fun. So how basic Paxos works, let's take a look. This is a consensus algorithms, right? Our goal is to have the machines to agree on one value. And I love to use examples to make the thing simpler. So let's think about how it works with humans. Let's say we are, after lunch, we're all gonna get together and, ooh, that's fun. We're all going to order one cake. We're gonna choose between chocolate cake and cheesecake. As a group, we can only choose one. How do we reach consensus? So how it usually works is someone in the room will say, hey, have we ever decided on which cake to buy yet? And then people will say, not really, we haven't decided yet. And then someone will say, well, let's go with cheesecake, because we love cheesecake, right? So this is basically how Paxos works. You have phases where a machine tries to prepare proposal by asking, has anybody ever proposed yet? If not, I'm going to now propose a value. So in basic Paxos, we have proposer and acceptor. Proposers are machines that propose a value to other machines. Acceptors are machines that either accept or reject a value from the proposer. So here's the process. As a proposer, the proposer will choose a proposal number. It has to be the largest number it's ever seen. And we're going to talk about how this number is generated later. And it's going to broadcast the number by sending this prepare message to all of the acceptors saying, hey guys, have you ever heard of any other machines yet? And the acceptor will then respond. And so the first thing it's going to do is going to check if the given proposal number that it received is it the largest number it has ever seen? If it is, then it's going to return a promise, basically saying, I promise that will only respond to your value if you have the number. If I don't see any number that is larger than yours later. So now if my proposer get a majority of response saying that, oh, now most people have accepted this number, then that means I have the largest proposal number. I'm going to go ahead and propose a value. So I'm going to send out this accept message with the value that I choose with the proposal number. And it's going to broadcast this to all of the acceptors. The acceptors will look at this proposal number again, try to make sure that it's still the largest number that it's ever seen. If it is, then it's going to accept this value and also update its proposal number. And if our proposal, again, received a majority of response from the servers, and they will check, have anybody rejected me yet? If any server rejected the request, that means its proposal number is not the largest number anymore. Then it will just repeat from the beginning. But if it didn't get any rejections, that means the value is chosen. So now we've all had a consensus. So now we can actually eat the cheesecake, hopefully. So how this proposal number is generated, we use two things. We use the server ID, which guarantees the uniqueness of the number. We also have a round number, which gets incremented over time and is shared among all the servers. So all the servers will remember the largest numbers ever seen. So we generate this new proposal number by incrementing the max round number and also concat it with our server ID, so to make sure that our proposal number is unique. Multi-Paxos is, we can think of it as an implementation of basic Paxos concepts. Instead of working with choosing one value, we want to work with logs and basically choose sequence of values so that we can work with the client. So it's a sequence of instances of basic Paxos, and each instance is a log entry in the log. So how it works is we have a client that will send us requests, and our leader will use basic Paxos to talk with the other machines and agree on one value. And it's going to wait till all of the command in the log entries are executed, and then it's going to execute the current command and then return the result to our client. So what's this leader and non-leader thing? So a leader in Paxos is a distinguished proposer. Basically, only leader can propose a value because we want the algorithms to make progress instead of competing with each other all the time. And the leader is responsible for sending heartbeat to other machines, basically saying, hey, I'm still alive, don't replace me, I'm still here, listen to me. And is also responsible for accepting requests from the clients. So if a non-leader did not receive the heartbeat within a certain amount of time, it's going to think that the leader has died. So it's going to step up and trying to act as a leader and act as a proposer. So, and non-leader, if everything works fine, if there's a leader still alive, the proposer is still working fine, then the non-leaders will redirect client requests to the leader, trying to let the leader decide what to do. So in Paxos, it's very unlikely to have two leaders at the same time because our round numbers and our the proposal numbers are mostly unique, and the leader IDs are all unique. However, the Paxos can handle multiple leaders. It just won't be efficient if we have two multiple leaders and trying to propose values, compete instead of making progress. So there are industry examples that implement Paxos-like algorithms, like Google Chubby and Apache Zookeeper. Today I won't have time to go through how Paxos are implemented in there, but I'm sure you can find lots of information online about that. So let's take a look at Raft. How is this different from Paxos? This algorithm is designed by Diego Ongaro and John Osterhott at Stanford. People recognize this as a simpler version of Paxos. In terms of performance and fault tolerance, it's equivalent to Paxos. When it was designed, not only the people considered consistency and correctness of the algorithm, they also designed this algorithm with a mindset of making it understandable for people who are implementing this algorithm. So why do we need to think about understandability? In most cases, when you design some algorithms, you want people in the industry to be able to use your algorithm. That means they really need to understand the algorithm before implementing it. And in distributed systems, a lot of the algorithms are already pretty hard to start with. So if you want people to twist your algorithm a little, to adapt it and extend it to their own system, to be able to really use your algorithm, you need to make it understandable so that people can actually use it. So compared to Paxos, Raft work around logs. And let's use the cake example again. Let's say we are trying to pick between cheesecake and chocolate cake. And what's your name, this gentleman sitting in front? Sorry? Alexander. Okay. So let's say in Raft, Alexander really knows how to pick a flavor of the cake. He's the master of picking cake flavors. So we're all going to trust him. We're going to say, Alexander, whatever you choose as a group, we're just going to listen to you. So in Raft, we pick a leader. Whatever the leader says, we're just, as followers, we just always listen to the leader. So that's basically how Raft works. So in Raft, we have leader election where we select one machine as the leader. And then we detect leader crashes. When the leader dies, we elect another leader. And then after a leader election, if we have a leader, we're going to have log replications. We are going to basically trust the leader and replicate the leader's log. And leader will process the commands from the clients. So as followers, we just always trust the leader. Raft guarantees safety. So it helps to keep the log consistent during election processes and also during log replication processes. We'll look at examples later to see how it really works. So basically, an overview of leader election processes. At the beginning, after machines have leader election timeouts, they will become candidate. When they become candidate, they will increment their own term. So we have this term number that we keep track of. Don't worry about this. We're going to have very specific examples to explain this process. And the candidate will vote for themselves, and they will also request other servers to vote for itself. So it will send out this request vote RPC to other servers. And there are three things that could happen from there. One is the server received a majority amount of responses from the servers, and basically the other servers mostly agreed to elect this current server to be a leader. In that case, the leader will step up and become a leader, and it will start sending heartbeats, acting as a leader to other servers. And it will also handle requests from the clients. What if it didn't become a leader? So what could cause it not become a leader? Basically, during the candidate election process, before it became a leader, if it received a heartbeat from a leader, that means someone else got elected. I'm not simply fast enough, so I'm going to step down as a follower. And now I'm going to redirect all the client requests to the leader and replicate the leader's log. I will act as a follower. And there's this third scenario where neither of those happened. So what happens is that there's a split vote scenario where it didn't get the majority amount of vote, nor did it receive any heartbeat from other machines. So in that case, the machine will time out after a certain time and re-enter the election state. We're going to look at that specific case later. So how do we know if the leader election works? We follow the following rules. We always definitely elect one leader per term. And each server can only grant one vote to one of the machines, including itself. And whoever received the majority amount of vote will win the election and become a leader. The majority amount of vote is the number of machines divided by 2 plus 1. So one example here would be if we have 5 servers in our cluster. If we have server 0, 2, and 3, vote for server 0. And if we have server 1 and 4, vote for server 1. In this case, server 0 will win the election and become a leader because they received a majority amount of votes from the other servers. So in leader election, there will eventually be a leader. At the beginning, I mentioned election timeout. What does it mean? So each server will receive this random number ranged from 100 to 300 to be this election timeout time. So after this period of time, they will become a candidate and start to gather votes from the other machines. And since this number is randomly assigned to the servers, usually one server will time out first, and the server that's usually timed out first will get the majority amount of votes and will become a leader. However, remember this split vote scenario that we talked about. How could it happen? So if two servers got the same election timeout accidentally, it doesn't really happen usually, but it happens, right? So in that case, we have two servers that time out at the exact same time. In that case, a split vote could happen. Basically, they both start to gather votes from the other servers, and none of them get any majority amount of votes. And in that case, they will time out after a certain amount of time and re-enter the election state, get another random election timeout number, and hopefully this time they will have different timeouts, so one could time out first and become a leader. Now we've talked about leader election. What about log replication? So during log replication, we'll have the client sending request to the leader, and what the leader will do is it will append this log to its entry, to its log entry, to its log as an entry. And then it will send out this append entry request to all of its replicas saying that I have a client that asked me to do this. Please do the same to your own log. Remember this command. And the replicas hopefully will get back to the leader saying that, okay, I got your request, I did it, whatever you asked me to do, I appended to my own log, here you go. And if my leader got a majority amount of acts from the followers, that means most people have known that such a command exists, then it's safe for me to commit this command in my log entry, which basically means that it's safe to execute the command and return the result to my client. And after I return the result to my client, I'm going to send another append entry request telling the replicas that, hey, I've already applied this in my machine. Please do the same in yours. So far we've talked about if everything works well. What if there are servers that don't even respond to the leader, or their server, they simply just didn't get the message? What will happen? So during the append entry request log replication process, if the leader tries to send append entry requests to the replicas, if the replicas, some of them, well, if the majority of them didn't respond to the leader, let's say, in this case, it only got one act back. If it's not majority, the leader will just keep retrying until it gets a majority amount of response. So what does log entry look like? It basically has three important things that we all have to know for each log entry. We need to know the current term which the command was received. Remember, we have this term number that basically keeps track of the election terms, and also the command that the client gave us during that time, and also the index of that log. We need to use them later in the examples. So our goal is to keep the log consistent. And if their server crashes, basically, it could cause our log to be inconsistent. So how do we detect that? How do we know? So this is an example of inconsistent logs. So basically, you have these three servers. 0 and 2 have longer logs, and somehow when 0, 1 is doing something at term 2, it just stopped working, and it has a much shorter log. So now we have an inconsistent log issue. How do we solve that? We follow the following rules in Raft to keep the log consistent. We definitely always trust the leader's log. We're always going to say the leader is always right. And we do not allow any holes in the log. That means when the client gave us command, we always append it to the end. We don't skip log entries. There's no holes in the log. Can you wait? Can you remember a question, please? Okay. And we always repair the inconsistencies in logs, in log replication processes. And if a log entry is committed, then we assume that all the preceding entries has to be stored in the log. And we'll look at how those two are achieved in the examples. So we have this log matching properties that we can use in Raft. Basically, for two entries, if you look at the example on the right, on your right, if you compare two entries, we compare two things. For S0 and S1, we compare the last entry. We're going to compare the index of the entry and the term of the entry. If they are exactly the same, like S0 and S1, they have the same, at the same index, they have two entries with the same term. If this is true, we can assume two things safely by using the log matching property. One, the two entries store the exact same command. Two, all the previous entries, including the current entry, are basically identical. That means we can be sure that 0 and 1 have the same log up to entry 5. Then the opposite example would be S0 and S2. At index 5, they have different terms. That means we cannot assume those two things. During log replication, we check consistency by sending this append entry RPC. We need the following information in the request. We need everything about the current entry, the index, term, and the command, for the followers to append it to their own log. We also need a little bit information about the preceding entry, which is the index and the term. So here's an example of everything you need to send to the other server. So what about an example? Let's say our goal in this example is that our leader, S0, wants our server, S1, to append log entry 5. So it's going to send the following information. It's going to send the index and term of log 4, of index 4, and then it's going to send everything about entry 5. And it's going to send it to S1. What S1 will do is S1 will check at index 4, do I have a log entry that has term 2? Yes, we do. And now I can basically use the log matching property, assume that everything up to 4 are identical between me and the leader. So now I can safely just copy what the leader sent to me. I can replicate my log, right? And what if it didn't match? What if at index 4 there's something that's not identical to the leader's log? So in this example, our S1 has an entry that is different from the leader's log. So it's going to compare at index 4, do I have a term that is the same as leaders? We have term 1, the leader has term 2, so no, they do not match. So we cannot say everything up to here are identical. So we're just simply say, I'm sorry, I'm not going to listen to you, because we have different logs. But previously, we did mention we always trust the leader, right? So how do we solve this problem? The leader will just simply go back one more. So instead of keep sending it 4, it will just move back to 3, and it's going to send everything about 4 and 5 as the current entries. And the preceding entry would be at index 3, the entry, basically the index number and the log term. So it's going to send all of those information to S1, and S1 will check, all right, let's check at index 3, do I have term 1? Yes. In this case, it matches. So now we can assume that everything up to index 3, our logs are identical. That means I can just copy whatever the leader has to my own log, because we always trust the leader's log. How do we guarantee, since we always trust the leader's log, how do we really guarantee the leader's log is complete? We basically have one thing that we have to always keep in mind. If the entry is committed, then all the leaders, including the current and the future leaders, have to have this entry stored. And we check leaders' log completeness during election state. We basically just simply don't choose any servers with an incomplete log. How do we guarantee that? So during this leader election state, when they gather votes, when they send out information to other servers to request other servers to vote for the leader, the candidate at the moment, they will send out this request to vote RPC, which has the following information. It has the term indicating which election term is the candidate is currently on, and the candidate ID, and its own last log index and its own last log term. An example would be, let's say we are the current state machine. We know everything about ourselves, and we received this request to vote RPC from the candidate. So this candidate is requesting me to vote for it. In this case, I received in the RPC the candidate's term is 2, my term is 3, and we have different IDs, but the following information are all the same. So in this case, do we accept or reject this request? Basically, do we vote for this candidate, and do we think its log is complete? So in this scenario, we reject it because we have different terms, and my term is higher than the candidate's term. That means I've probably been through more election terms, and that means my log is more likely to be complete. So we reject the vote. We simply don't vote for the candidate. What about in this example? If we have the same term, but this time we have different log index. So my log index is higher than the candidate log index. What do? Do we vote or not vote? Well, if you look at the index, right, I have a higher index. That means my log is longer. So I cannot give my vote to someone who has a less complete log than myself. And in this case, we reject a vote because our log is longer. That means our log is more complete. What about in this example? We have the same term and then different index, but this time the candidate index is longer or is higher. Well, in this case, we do vote for it because its term is at least large as mine, and its log index, oh, there's a mistake. Their last log index is larger than mine. So that means their log is probably more complete. So I'm going to vote for this candidate. Well, consensus algorithms help us to solve a lot of problems, but they're not the solution of everything. There are certain things that we have to consider in distributed systems. Well, first of all, we say that we have consensus by communicating with each other. So we rely on messages. And when we send out messages, there's a high amount of overhead. And we also have to consider, what if we have duplicate messages? How do we handle out of order messages? Do we care about messages that are out of order? What about messages that get lost? How do we know that, and how do we deal with that? What if there are different components of your network are super far from each other? What if you have network latency? How do you deal with those issues? We also have to think about failures, right? We could have leader failures, we could have replica failures, we could have network partitions, and how do we guarantee the availabilities of the machines? What about security? Who have the right to read and who have the right to write? How do we know that? So building a distributed system is extremely hard, and building one that works correctly is even harder. How do you prove that your system works well? How do you know that it works without any problems? If there are bugs, how do you debug it? There are also other problems that could happen. How do you deal with crash loops? Basically, your computer goes crash, comes back, crash, comes back, crash, comes back. How do you deal with those kind of problems? There are also application level problems. You could get corrupted data. How do you know that the data is corrupted? How do you handle data that are corrupted during the process of sending them? So the issues that are mentioned above, partitions, network delays, packet losses, blah, 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 those could be handled by your consensus algorithms if you design them or if you implement them with the mindset of thinking about those problems. However, there's one problem that the Paxos and Raft that I described before cannot handle, is this Byzantine generals problem. So what this is basically you have two generals. They're gonna decide whether to attack a city or retreat from it the next morning. And they can only communicate with each other by sending messages to each other through a liaison. And they cannot directly talk with each other. So basically, if they both choose one decision, if they both choose to attack or both choose to retreat, then they will win the war. However, if they choose differently, they will lose. This problem doesn't sound very hard to solve, right? But the problem is we don't know if the other general is a traitor or not. So we can't really trust whatever the other general says. What do we do? How does this problem get applied to distributed systems? We have Byzantine failures in the system where basically we have a node that acts normally. It could still send messages, it could still respond to other servers, but we just don't know whether it's a traitor node or not. We don't know whether it's malicious or not because it acts everything normally. It just acts like another server. We can't really tell, right? So this malicious node could send messages that corrupt other nodes. So the Raft and Paxos that I described before, basically the overview of those two algorithms, those two algorithms cannot handle malicious or misbehaved peers. So the ones that I described can only work if you trust the other nodes. They work in a non-Byzantine environment. Having one node that's malicious may not be capable of destroying the whole algorithm, but it could corrupt the application level data, and it could inject malicious values in the application. So our application could be abused. In this case, we cannot really guarantee the confidentiality and the integrities of the system. Are there anything that could help us solve this Byzantine failure problem? Yes, there are Paxos and Raft modified versions that could handle Byzantine fault-tolerant algorithms. But the problem with those algorithms is that they have an even higher overhead. Solving Byzantine failure is very expensive. So when you're choosing algorithms, yes, it's good to have your algorithms really reliable, but it's also very expensive to do it. It comes with a cost. So what have we learned from this talk? Well, in the industry, if you're trying to implement a distributed system protocol or trying to implement a consensus algorithm, well, the first recommendation is try not to do that. Because implementing an algorithm compared to understanding an algorithm is different. It's much harder to implement one. There's so many issues that you need to think about. And you need to test your system to really make sure that it works. And we all know that testing distributed systems is ridiculously hard. So try to use someone else's work. If it's been tested, if it's been proved working, then try to use other people's algorithm. And if you do have to implement a consensus algorithm yourself, you need to think about, is my algorithm resilient against the issues that we've talked about? And do we want it to be resilient? For example, Byzantine fault tolerance, right? Not all the system needs to be Byzantine fault tolerant. It's always a trade-off between reliability and complexity. So when you're building your own system, you need to think about, do I want to handle those issues? Is it worth it? How do I handle it if I do have to handle it? When you're designing, in the academia, when you're designing consensus algorithms and distributed system protocols, you need to not only think about the correctness and the consistency of your algorithms, you also have to consider the understandability. You want people to use your algorithm to be able to understand it and therefore implement it correctly, to be adapted to their environment, to be used in the industry. So not only we need to think about everything, including correctness, complexity, consistency, we also need to make the algorithm understandable to people. And hopefully this talk helped you all to understand a little about how computers have consensus between each other. And thank you for your attention. Now I can take questions. And they said there's a mic that will send around.
Mic's right here. We have 3 minutes left for questions.
Okay. Yay, I follow within 40 minutes. Okay, anybody have, do you still have? Okay, yeah, usually the questions will be answered in the later slides, because the 2 points, right, yeah. That's why I was like, could you wait a little? Yeah. Yeah.
How does consensus work for leaderless systems?
How-
Systems that are leader.
What do you mean? How does consensus work for leaders?
Leaderless systems.
Leaderless
Yeah.
systems. Well, different protocol have different ways of dealing with it. And it depends on specifically which one you're talking about. So if you're talking about peer-to-peer, maybe?
Yes, like Dynamo style databases, for example, where you don't really have a leader, but you reads or based on like.
I think that really depends on the protocol, but I'm trying to think how, for example, like BitTorrent, it's peer-to-peer system, right? So they exchange information. They basically don't have the central server that knows about everything. They exchange information by communicating with their own peers. And different algorithms have different ways of achieving consensus. Yeah. I think, I'm trying to think. It's hard to describe the general process without a specific algorithm because they all have different ways of solving the problem. Yeah. Yes. The mic.
I remember Academia, speaking of this distributed algorithms.
Yeah.
Academia routing is vulnerable to an attack. And has anything happened in the last maybe 10 years about Academia, how to make it resilient to this kind of attack? Or?
So, like, has any attacks, like really bad attacks, happened in the last 30 years? You're asking?
Well, yeah. Well, with Academia, you can break the whole system by just lying, repeatedly lying.
Right. So there
Yes.
are Byzantine fault tolerance systems. There are algorithms that deal with Byzantine fault failures, but implementing those algorithms are pretty hard. Leslie Lamport wrote a paper on designing a Byzantine fault tolerant Paxos. That describes how a modified Paxos that is resilient to Byzantine fault failure works. It's a different protocol, but it's much more expensive in terms of complexity and overhead. There are algorithms that deal with Byzantine fault failures. Yes. Anybody else? No? Okay. I will be outside, and anybody could just come and find me if you have more questions. Thank you.